알겠습니다. 감사합니다. That's right. I supposed to speak it Korean, English. I'm sorry. All right. Thank you very much for joining in the early meeting, and thank you for the nice introduction, Professor Che. So without further ado, let's dive into the topic of the talk. All right. Okay. Sorry about that. So today I want to present several work from my group about the low power keyword spotting hardware design. And probably most of you will be familiar with the keyword spotting already, which is essentially try to catch up a keyword, and then once the keyword is, the device can catch up the keyword, they can exercise a more complicated, processing such as speech recognitions, right? So, keyword spotting is very universal, and you can definitely know that you have such a feature in your smartphone. But now it's actually going into other areas as well, because the voice interface is such an attractive method to communicate between machine and human, right? So for that reason, keyword spotting gaining quite a bit of attention for the last 5-10 years. So let me briefly introduce how the signal processing chain look like for keyword spotting systems. So it generally consists of the 4 different components. The first component is the analog feature extraction, and the second component is the analog to digital converter, followed by the feature extraction, and then finally the classifier, right? And finally the classifier produce the result that this is keyword or not keyword. So I will then introduce how the signals actually look like in all these channels. I mean, all these components. So first, as you probably expect, the speech signals is the analog signals, meaning it's continuous time and continuous magnitude, and generally produce the either voltage or current value from your microphone. And these time varying signals goes into the analog front end, and analog front end essentially condition it so that it can perform the follow-up process. So here condition usually means the filtering, so it usually cut off some of the unnecessary bandwidth, unnecessary frequency component, and also it amplify the magnitude of the signal so that the follow-up circuit can process. So once signal comes out and from AFE, analog feature extraction, analog front end, it goes into the analog to digital converter, and this converter essentially converts this analog signal into digital code, digital streams, right? And now the signal is the discrete time domain and also discrete magnitude signals. And after that, what they do is they do this feature extraction. And feature extraction, most commonly used method is so-called spectrogram. And spectrogram is essentially spectrum transient waveform, meaning x-axis is the time, and the y-axis is your spectrum frequency component, right? And then what usually done is, they grab a small box of the spectrogram of the heat map essentially. And this matrix is essentially my feature that goes into the classifier. And classifier look at this spectrogram heat map, particular section of the spectrogram heat map, and based on the shape of this heat map, they recognize the keyword or non-keyword, because a keyword has a specific shape and non-keyword has a, some strange shape that is not really related to the keyword. So that's the basic idea how these keyword spotting system works. Okay, so keyword spotting has been a very popular topic in computer machine learnings and AI and hardwares and systems. And I have some quick survey of the recent state of the art in terms of the accuracy of the spotting accuracy on the x-axis and the power consumption on the y-axis. There's many different data points, and you can see that on the top part of the plot, there is a several square, hollow interior symbols, right? STM32 and Symbian M44. And as the name implies, these are the software implementation on the microcontroller, right? So if you do software implementation, the state of the art essentially showing something around 1 milliamps, 1 milliwatt, or about hundreds of microwatt power consumption, which is great. And their accuracy level is range from 85% to 90-something, 95% kind of accuracy you can see. So that's the kind of software implementation on the low power microcontroller. And then you can see some of the interior, the solid interior symbols. Some of them are spheres and some of them stars, right? And they tends to, these are the ASIC hardware implementation, so silicon implementation, right? And you can see that their power consumption is usually several orders of magnitude lower than software implementation. But there's also one symbol. I have a star mark here, right? And the difference between star mark and this square symbol is star mark actually contains every component that I show in the previous slide. So analog front end, analog to digital converter, and then feature extraction and classifier. Whereas these square symbols only represent, including the digital component, meaning feature extraction and the classifier. So if you look at the end-to-end system, essentially the state of the art is about consume 10 microwatt, and the accuracy is around 90% or something, right? So that's kind of a state of the art in the keyword spotting, hardware design. So then maybe you can ask a question, right? Okay, Professor, you are trying to reduce the power consumption from the device that consumes about 10 microwatt, right? Do we really need that, right? Because if you look at your phone, your phone has an enormous size of the battery, right? Half of the entire volume is filled up by the battery, right? So for such kind of system, probably you don't really need, reduce the power consumption below, 10 microwatt, right? However, there's emerging devices like IoT and smart homes, robotics and all of this. They definitely demand a more, orders of magnitude higher power efficiency. So here, one example I can bring up here is the door sensors, right? This is the small device that you can buy maybe $20 and put it on the door and then make sure that your door is closed, right? So that you feel secure, I guess. And this door sensor also contains other features like temperature sensings and humidity sensors and light sensors. And so it's quite a nice device. I actually have 5 of them in my lab. And this device definitely have a very small form factor because you don't want to put like gigantic door sensor in your door, right? And the price is also very sensitive, right? You can sell this one for $100. This has to be very, very cheap. Even $20 is quite expensive, right? So they end up having very small battery, and this battery is like a typically coin cell in the range of 5 to 20 millimeter diameters, right? And with this kind of battery, how much lifetime you can have? We did a quick survey here. This plot shows the necessary power consumption, on the y-axis, and the lifetime that you want to have, right? So in this plot, if you assume 5 millimeter coin cell battery, expecting to have a 1 year's of lifetime, what we need is less than 1 microwatt power dissipation. And definitely, I'm happy to pay more if it lasts more than 1 year. Because we live in a house that for more than 10 years usually. So 10 years of lifetime, then it's like tens, hundreds of nanowatt. So that's the kind of demanding challenge on the power efficiency side for this type of features. Okay, so from now, what I'm going to do is I'm going to introduce some of the work that we did to reduce the power consumption. And first, we start with the analog front end and data converter, followed by the classifier, and then finally the system end-to-end operation. So first, let's talk about the analog front end and the data converters. Okay, so I redraw the same things that I showed in the previous slide, essentially the process step of the keyword spotting system. It starts with the RNA, analog to digital converter, and digital feature extraction, and then digital classifier, and the result coming out, right? And here I put some frequency number on top of it, and this is sort of represent the speed requirement of these circuits. So what I mean is, okay, for the human voice, most of the important information is limited up to 5 kilohertz. So RNA visually we design to have a bandwidth of about 5 kilohertz. Apparently, if you want more higher quality of the sound, you can design 16 kilohertz, 32 kilohertz, whatever you want. But for this type of application, 5 kilohertz turns out to be okay. So RNA, the design, the bandwidth target is typically set to 5 kilohertz, right? And and the ADC, now your ADC sampling rate needs to be twice of the highest frequency component of the input signal based on very famous Nyquist rate, right? So in other words, ADC needs to sample the output at 10 kilohertz, right? 10 sample per second. That's what 10 kilo sample per second. That's what we need. And this followed by the digital feature extraction, and feature extraction is generally filters or FFT. And what that means is actually this feature extraction also needs to process the data, these samples at the same rate as the ADC. So it is also operating about 10 kilo sample per second kind of operation. And finally, the digital classifier, take over the output, and suddenly we see much smaller number here, right? 50 hertz. It's not 50 kilohertz. It's a 50 hertz, right? So there's about 200x difference. The reason is, if you remember, I showed the spectrogram in few slides ago, right? This spectrogram is not like sample by sample thingy. It is actually over 25 millisecond window or even wider window. So in other words, digital classifier get the new input much slower rate than the signal samples, right? So digital classifier, in the end, are operating much lower frequency. It's not like a clock frequency. You can still have a higher clock frequency by reusing your hardware, but the data rate that it produces is much lower than all the other three components that we have. So in light of this, we're gonna see that this architecture is not very optimal for ambient sound detection operation, because we all know that most of the time there's no sound, right? How many times you actually call your phone to start the speech recognition, right? I mean, maybe 10 times a day and most, right? Most likely only 1 or 2 times. So most likely they don't see any sound for 99% of the time. However, if you're just following this conventional processing step, then there's a huge amount of power waste, because everything runs at worst case speed in some sense. So based on this idea, what we try to do is actually swapping the feature extraction with the ADC, right? So instead of put the feature extraction in digital domain, what we can do is put the feature extraction before the ADC in the analog domain, and then process the conversion of the feature, not the signals, right? So now the ADC needs to only operating at 50 hertz instead of the 10 kilohertz. And that's the significant savings, because ADC now consume significantly lower power. Then the question is, how are we going to make the analog feature extraction circuit, right? And the good thing about the speech is these features are spectrogram, which is the frequency energy component of the different band, and that can be easily done. In fact, I mean, not so easily, but that can be done with the analog circuit. Analog circuit has a filter, analog circuit has a rectifier to accumulate the energies, and so on and so forth, right? So definitely this is possible, and that's the direction that we headed in about 2017 actually. So quite a bit of a while ago, I guess. And with this concept, what we design is this architecture. So it starts with the microphone on the far left. And then there is, sorry, my keyword spotting just taking action. And there's the LNA, which is the same, I guess. And then after that, we have a bunch of analog feature extraction stage. And that stage has a 16 different channel, because we're going to look at the energy component of the 16 different frequency band. And that's each channel start with a bandpass filter, which filter the signal, and followed by the rectifier, which convert the signal into the energy of the signal. And then that is essentially the end of the feature extraction. So rectifier, full wave rectifier, produce the current, and this current magnitude represent the energy component of the specific frequency band, right? And after that, this frequency energy going into the integrated and fire neuron IAF, and this IAF essentially produce the spike proportional to the amount of the current it received, right? So IAF, which is very simple circuit, is actually works as your analog to digital converters. And the output of the IAF is your spiking rate, and this spiking rate represents the feature vector or feature matrix that you are interested in. And then we going into the digital domain by counting this spike. And after that, it's just following the conventional digital computation process to perform the classifier. So that's the high-level architecture. And in the end, there's a fairly we need a fairly skillful designer to design all this circuit. So apparently, I can't really explain this in a short amount of time. But our postdoc and our graduate students were able to produce the very nice low-power analog signal processing circuit, which is actually not new. Actually, it's fairly old technique, has been abandoned for a while, I guess. So not many people can do it anymore, I guess. But with the new interest, going up, maybe there's a more need for this skill. So anyway, the chip is taped out in 0.18 micrometer CMOS technology. And the total area of the thing that I show or in previous slide is about 1.5 by 1.6 millimeters square, which is quite tiny actually. And we compare our work and previous work in terms of the feature extraction efficiency, right? So for the first column is our work, and the second column is the digital feature extraction. Doesn't have an ADC. Third and fourth column has the ADC and the feature extraction stages. And as you can see, there's about 10 to 20x power savings in the gray row. Power per channel is 24. So there's about 10, 20x power savings that we achieve with this simple swapping and also designing of analog circuit to extract the features. All right, so that's great. So we published a good paper. People get excited, and we look back again, I guess, because we want to do another project, I guess. so we do another project, and then we want to do another project, and then we look at our own design, right? Okay, this is the power breakdown of my analog mixed signal circuits, right? So I have a LNA, I have a bandpass filters, I have a full wave rectifier, I have integrated and fire neurons and bias generation circuitry, and 95% of the total power is consumed in the analog front end and the feature extraction, not the A to D. Because A to D is just optimized drastically, so it only consumes 3.4%. So that's great, but at the same time, this is a new challenge because now I want to optimize the analog front-end circuit so that we can get the more balanced and overall low power consumption for all the analog mixed signal hardware circuit. All right, so then how are we going to get to that, right? I mean, in fact, we actually want to do another 10x power savings from what we've done. Previously, we about achieved a 300 nanowatt, by the way. So we want to achieve another 10x from what we did. So we're looking for paths toward that 10x power savings, right? And in general, in circuit design, right, if you want to reduce something or improve something, you want to compromise something else, right? But what to compromise is the first primary question that we have to answer. So what design constraint we want to relax, right? That's the big question that we had about maybe 2 years ago, 3 years ago, right? So we look at the traditional, or very important constraint of the analog circuit design. The first one, everyone knows is the noise floor, right? We designed the analog circuit to improve the signal ratio above the noise floor, right? And if you're raising the noise floor, you expect to receive quadratic power savings, right? These are related to voltage swing, in fact. And so what we did is we kind of raising the noise floor until we get the 10x power savings. And we did a simple experiment on our circuit, and what we found, and then run the neural network simulation to see how much it actually affects my accuracy of a classifier, right? So what we found is apparently not good because in fact, if you raise the noise floor, we end up losing quite a bit of accuracy from, let's say, 95% to 90% or something. So that's not good. So we move on to the other design constraint. The second one that we look at it is the, probably something that everyone also look at is the bandwidth, right? Okay, your circuit bandwidth is directly related to your power consumption because circuit bandwidth set the bias current level and the capacitor size, right? So what we try here is the same thing. We reduce the bandwidth of the circuit until we get the power saving of 10x, right? And the result, and then look at the accuracy again. And unfortunately, this doesn't work either. Okay, so we reduce the bandwidth, accuracy goes down together. So fine, it's not something that we want to do. So finally, what we look at it is the linearity. So linearity is something that is related to the input and output, right? Amplifier design, analog to digital converter. A lot of designers spend nights and days to improve the linearity, in fact, right? Because the linearity happened to be the mantra of the analog circuit design, and they somehow want to improve the linearity a lot. So we kind of break the mantra and then see, okay, let's just reduce the linearity, relax the linearity, and then just reduce the power, and then see how it affects. And surprisingly, or actually quite expectedly, the linearity actually doesn't affect, or we can compensate the accuracy from linearity fairly easily. In fact, this is actually, something analogy to the biological system. Biosystem is not linear either, right? And we, however, can do very good job for the recognizing bunch of different speech signals and so on. So we are kind of expecting this might be the one, and it turns out to be the one that we want to relax in our design process. Okay, so with this new relaxing, finding what to relax is easy to design, right? Because you just make the design very poorly, right? So in the left side is the LNA designed by our postdoc, Dr. Minao Yang, and published in ICC 2018, right? There's a tons of transistors and tons of components that looks like a capacitor and also some resistor. They are not real resistors, some of the pseudo resistors, some of the poly resistor. It is requires a lot of tweakings and careful architecture job to ensure that this old circuit operating at 0.6 volt, which is fairly low for analog circuit, right? We have a almost 5 stack here, and some of them definitely in the triode. So you'll be surprised, and you'll be a little bit scary about it, I guess. So these are fairly delicate, complicated design, right? And now we decide not to do the linearity thing anymore, and then we take the single-ended design. We just put the LDO on top of it so that we can compensate the power supply noise, and then do the very simple design. And then it turns out to be orders of magnitude simpler, and then also quite power saving too. So we apply the same concept of this, just to get rid of the linearity, and then do the same design for the bandpass filters and the rectifiers and amplifiers, and then all the other circuitry. So for example, amplifier, right? Amplifier, what we did is actually we limit the output range, right? In analog amplifier design, you want to have a very gigantic output range, right? Because they're going to help us the ADC a lot, right? However, what we do is we just limit the output range, and when the output is too high, it just clipped, right? You can see in the waveform, the black is the ideal result. It amplifies all the way to the top and bottom. But what we did is just to make the asymmetric clipped amplifier. It goes only up to 300 millivolt in the positive side, and it only goes down to minus 150 millivolt in the negative side, right? So that's fairly improper design, by the regular designer's eye. But it turns out to be it works fine and also consumes a lot of power, saves a lot of power. I'm sorry. So with this concept, we design another test chip now in the 65 nanometer technology. So this chip is about 1 by 1, and there's the LNA and analog domain feature extraction, essentially bandpass filters, amplifiers, rectifiers, and so on. And then we also have an analog to digital data converter, essentially the integrated and fire neuron, followed by the DNN classifier. So now go back to the analog front-end circuit design, power consumption breakdown. The left one is the one that I presented in the first work, right? Consume about 373 nanowatt, 95% of the power consumed by the analog circuit. In the second version that we have, where the linearity is severely constrained, now the relaxed, the total power consumption is only 60 nanowatt. now everything is more balanced. So we about achieve a 6x power reduction by taking this non-conventional route that relaxes the linearity. All right, so we are right on track, and now we are going into the classifier, right? So my background is actually digital circuits, so this is more convenient area actually for me, a comfortable area, but anyway, we need to focus. I mean, we need to do everything in fact because the system is consists of many different components. So okay, classifier. So classifier, let me briefly introduce the some of the knowledge that probably most of you are already familiar with. Artificial neural network, right? Artificial neural network is the most popular neural network that essentially backbone of the deep learning, convolution neural net, LSTM, everything pretty much, right? And artificial neural net, the name itself is no longer used much because it's quite old. Right, it started from like 1970s or something. It's quite old. People don't really use it, but essentially all the neurons in these popular network is artificial neurons, right? And artificial neuron does a very simple job. What it does is it has multiple inputs, right? And these input values are accumulated, and then they perform some function, right? So these are kind of a simple mathematical operation, and in digital hardware design, what they do is they perform this computation all based on 2's complement binary numbers, right? So n-bit binary numbers. For example, if I want to represent 4, if you remember your basic class, it will be 0, 0, 0, 1, 0, 0, right? So they are based on this number representation, and they just perform the additions and multiplications and so on and so forth. So that's the artificial neural network. But as a researcher, we want to always looking for some exotic things, and the spiking neural network is the new thing that emerging on the horizon about maybe 10, 15 years ago, right? So spiking neural network, it sounds more spiking, and it is actually, however, does almost the same operation. So what it does is actually integrate the spike and number of the spike, and then if it integrate too many integrate enough spike that is beyond the threshold, it fire the output spike, right? So that's how it works. And the key difference here is actually how you represent a number or how you represent the value, right? So there's many ways and many different spiking neural net, but most popular approach is actually using the spiking rate. So for example, if I want to represent the value 4, what they can do is they sending or creating the 4 spikes in a given time window. It could be 1 millisecond, it could be 1 microsecond, it could be 1 nanosecond, but essentially they represent the number as the number of the spike. And this is actually interesting because what it means is actually if the value is the 0 or there's no input, like a keyword spotting case, then there's no spike and in the hardware, and that means there's no switching power dissipation in the hardware. So this gives you a potentially a route to reduce the power consumption on digital hardware in a very low level of the activity, right? So that's kind of interesting, and then that's the route that we take to implement some of these keyword spotting classifier. Okay, so I'll briefly introduce some of the prior work. The first work is the IBM's TrueNORS in 2014, right? So these are very famous ZS1 processor, right? And it is asynchronous SN, meaning it is really a spike kind of stuff, right? However, the downside, and this to me is that it utilizes the asynchronous logic family. So asynchronous logic family is not really used much nowadays, but if you actually look at some textbook and see their circuit, it is actually pretty big, and it is based on the domino logic. So domino logic, which has a pre-charge and evaluation phase. So it's fairly power hungry and area intensive, and also problematic for voltage scaling. Doesn't work very well for the scale technologies, and so on and so forth. And end up they are consuming milliwatt, which is orders of magnitude better than the CPU, but still consumes quite a bit of power, right? So because of this reason, some of the people start to design, synchronous version of the spiking neural network. So, okay, synchronous version, right? It has a clock, and since we have a clock, we can use the static CMOS logic, which consumes very low power and very robust as well. However, this clock runs all the time. And by the way, this is the work by the SNU in 2019 IACC by Professor John's group. And it consumes still tens of milliwatts, right? So that's the kind of situation or current status of this SNN hardware design. So what we propose is actually we are trying to do spike-driven synchronous. So we're going to still do the synchronous in some sense, but we're going to be driven by the spike. So what that means is we're going to design our neurons such that it can actually start its own clock based on input spike. So input spike arrives, it starts the clock, perform the necessary action, and then once the action done, they shut down their own clock and go to the sleep mode. So it is kind of a clock enable and clock disable scheme all driven by the spike. So it requires some delicate digital circuit design, but this can be done with a reasonable amount of hardware overhead. And we end up actually getting the neuron that works at about hundreds of picowatt per neuron, which is very low actually, which is actually close to the biological neuron power consumption, which I want to talk about a little bit later. And the other interesting characteristic is that actually the power consumption is again, scale with the input rate. If you have a lot of spike in the input, it consumes a fair amount of power. But if the input spike is very low, it consumes much lower power. And this is particularly good for keyword spotting because we know that most of the time there's no speech. The input has a very sparse period, right? So that's the essentially the idea that we pursue. Okay, so based on this circuit design, we essentially proposed spiking neural network chip that has the 5 pre-connected layers. Has about 600 neurons in it, and then there's about 10,000, 60,000 synapses in it, and they essentially we can program the weight and we can program how many neurons can be used per layer, and then generally map the simple classifier models in this spiking neural network. And again, this is fully designed by this spiking-driven synchronous approach, meaning all the component is enable and disable autonomously based on their input spike activity. All right, so the chip is fabricated in again 65 nanometer CMOS, and the core area is about 2 millimeters square. And we measured the chip, works fine, and we compared the prior work, right? I mean, I briefly already mentioned the PARC IACC 19 is the one from SNU, which is the synchronous version of the SNN. 10 VLSI 18 is also synchronous version of the SNN. And the True North is the one of the well-known asynchronous version of the SNN. And they are all consume tens of milliwatt, whereas our things actually consumes 300 nanowatt. So there's about 10 to the 4 power reduction here. And this is sometimes a little bit different design target in some sense, right? Because these prior work is more targeting like high performance, high throughput inference engine, whereas we are more like ambient, a continuous, always on intelligence hardware. So it's they are doing their own their best job to optimize their own core. We do our own core, and this is another extreme of the design point, I would say. All right, so here one thing I want to briefly mention is actually our chip contains 650 neurons and consumes about 300 nanowatt, right? And that put us into something around 461 picowatt per neuron, right? And if you actually look at the human brain, it has 86 billion neurons and consumes about 20 watt, right? If you divide it, it actually turns out to be 232 picowatt per neuron, right? So this is very exciting in some sense because we are getting into the region that actually the silicon neurons are close to the power efficiency of biological neuron. Apparently, the caveat here is that we have only 650 neurons, whereas the human brain has 20 billion neurons. And potentially human brain can have, brain neuron have a more complicated functionality than our neuron. So, I think, biological neuron wins, over our silicon neuron, but, unless we are getting to that, picowatt power consumption region. So exciting to see, but, there's a long way to go. Okay, so now we are going into a little bit, different direction, but also very related to the direction, right? So I'm talking about so far, how to reduce the power consumption, and it end up consume, hundreds of nanowatts, right? So, if you combine analog program, feature extractions, A to D, and then classifier that introduced so far, combine all together, it definitely less than 1 watt, 1 microwatt, right? So that's the, already something that we achieved. But at the same time, if you actually consider to put this into the practice, right, in the real field operation, you probably not be very confident that this circuit is actually going to work, right? Because this circuit is like babysitted in some way, and their inputs and outputs are very nicely calibrated, and then push it into the device and so on, right? So these are kind of academic vehicle in some sense, right? And once you put the real world, then there's many different problems there, right? The signal is, for example, not very clean, right? And this is the big problem, and then they're gonna potentially lose a lot of accuracy there. So the next question that we had was, okay, we do a lot of good job in power efficiency, but can we still maintain these things to work in the real world, right? So how are you going to improve the robustness, right? Our classifier is probably not going to work even there's any noise, right? So look at this situation, right? Okay, speech signals is not clean, right? Most likely they'll be corrupted by the background noise, right? You drive the car, sometimes there's car noise. You walk in the street, there's people chatting each other, right? There's a lot of noise out there, and these will affect your classification accuracy. So people typically, one way of the straightforward, well, not really very effective, but one way to deal with this is the noise-dependent training, and that's essentially make the data set that contains the target noise scenario, right? So you create the data set that train the classifier, but mix with the noise, I'll expect to see car noise of 10 dB SNR, so just mix it and then use it for the training, right? So that's the noise-dependent training. And we did it, and we did a small experiment here. So x-axis the test data SNR, and y-axis is the accuracy, right? And we trained this classifier with a 10 dB SNR metro noise mixed input data set, right? And once training is finished, we use it for same noise type, but different SNR. See whether the classifier can tolerate lower SNR or higher SNR. What we found is, okay, if you go from 10 to 20 dB, classifier has no problem. It actually gains a little bit of accuracy there. But if you reduce the SNR below the target level that we use in the training process, it drastically reduces the accuracy. So here you can see that the accuracy is about reduced by 30% from 95 to the 65, and that's a significant reduction. And this is typically considered as fail. Right? It doesn't work. So this is the big issue that we found. Right, and what about the other types of noise, right? I only do the single noise in the previous experiment, but in the world, there are so many different types of noise, and they are all mixed together, and then causing problem in your classifier. So for example, restaurant noise, even lower SNR, and so on and so forth, right? So if I do that, I train only one noise and then test it with the different noise, right? And then I'll get another 50% reduction in my accuracy. In other words, my accuracy is 50%, right? And this is keyword spotting, right? So meaning it just barely works better than random flipping of coin. So essentially, this noise essentially make the classifier completely fail. So how are we gonna address this, right? So in a lot of cases, what people do is this noise independent training, and what that means is they again it is also called the data augmentation. So they essentially make a lot of noise, all the possible noise, all the possible SNR level that you can see, and then feeding into the data set. So now your data set is gigantic, and then train the classifier based on the data set. So this approach is generally working well for cloud system, right? Where you have 100 GPUs, and you have 100 CPUs, and probably hundreds of gigabytes of memory. So for such a system, network is probably like unbelievably large and deep. So you can do this kind of a training, and then it works fine. However, we are targeting low power device, right? And we don't have that many parameters in our model. So if you try to do this noise independent training, it doesn't work. It just blow up the model, or you not make the model to learn all the different data set here. So that's the challenge, and we need to come up with a better idea than the conventional data augmentation technique, noise independent trainings, and so on and so forth. Okay, so move on. So we go back to our signal processing chain, amplification, feature extraction, and feature coming out, right? And usually what the problem is that feature is not robust, meaning feature varies too much with the different noise characteristics. So what we need to do, we believe, is actually we put some additional stage after the feature extraction before classifier, such that they can try to make your feature more robust across different noise. And what we came up with, the idea of this divisive energy normalization, actually inspired by a biological system. So let me talk about this divisive energy normalization a little bit here. So what does this divisive normalization do? So I don't have an equation here. There's an equation, but what it does is essentially input comes in, right? In features comes in, and then we perform the low-pass filtering of this feature, right? In other words, we perform the average calculation, right? Moving average calculation. And then this moving average value will be my denominator, and then I'm gonna divide my input with this denominator, with the filter value. So value comes in, the previous value, average value will be, the input value will be divided by the average value of the previous input. So that's the basic idea of the device normalization. Actually, equation is a little bit more complicated than that, but that's the essence, right? Low pass filter, and then using that value divide the input. Right? So that's the idea. So and this process is actually perform the whitening noise. What that means is actually make the impact of the different noise on the feature similar to each other, right? So I'll tell you what that means. So this picture shows our experiment. So there's a 2x6, a 2x3 plot, and the top row is the conventional feature, just MFCC feature, mel frequency feature, and the bottom rows are representing the proposed divisive normalization, feature. And the three different columns represent the different noise mixed into the signals, right? The first one is the traffic, metro, and final one is the white noise, right? So we mix the three different noise and perform the feature extraction using two different methods, conventional and proposed. And here we actually perform the covariance calculation of the these features and showing this map of the covariance, right? As you can see, in the top row, they all look similar, but they're actually quite different if you look at it, right? There's some, higher, a lot of part is like a black, but there's also very different colors in some important point here and there, right? Whereas if you look at the bottom, these are more kind of similar pattern that you can see. In other words, if you actually perform the divisive normalization, the feature, the impact of the noise on the feature become similar to each other. And what that means is the classifier can actually learn smaller number of patterns instead of the large number of patterns. And that reduces the size of the classifier and also improve the accuracy of your classifier. So that's the key idea. And I have a few more comments here. I already mentioned, divisive normalization actually found in biological sensory processing circuits. It is actually inside of your, I think it's actually olfactory system, your nose system. And it is also considered to be, I don't exactly know it is in the eye, but I'm very sure that it is in the olfactory system. So these are biological sensory processing circuit and is inspired by this, actual biology. And if you study the deep learning, or artificial neural network, low pass filters and division is very rarely considered in ANNs and then CNNs and deep learning. The reason is division is computationally expensive, right? Division is 10 times more complicated than multiplication, right? And multiplication is 10 times more complicated than the addition. So most of the digital signal processing end up doing, adding and subtracting because it's cheap. And also if you do the multiplication, usually you multiply with a constant multiplier, right? You multiply something with a constant, but because it helps simplify your multiplier hardware. So then maybe someone asks, okay, you do the divide, you need to do the divider. Why you just do the 1/k multiplier instead of the k divider, right? The problem is here, the k is the low pass filter version of the input and change all the time. So we can really have a constant multiplication instead of the real divisor. So we end up having really a divider. So then another interesting part that we found was actually in SNN, divider is very easy to implement. Simple integrated and fire neuron can implement the divider in the spike domain with only handful of the transistor. For example, let's say I want to divide by number of 3, right? What you can do is just counting the incoming spike, and every 3 spike, you produce the 1 spike out. Then you're going to perform exactly the divider that, division by 3 with this simple integrated and fire neuron in the spike domain. So that's the idea that we like to pursue, and we end up making actual circuit based on this concept. So here, the first chip that's shown on the left is called the NAPE chip, and this is the 2021 IACC by Wei Wang, and it's a 65 nanometer and takes about 0.72 millimeter scale. It contains the analog RNA and the analog signal processing circuit that we talked about, the feature extraction, and the analog to digital converter, and finally this divisive energy normalization circuit that we just discussed, right? And it followed by the classifier, which is we previously taped out in SNN in the Wei Wang AACC 2020, and it takes about 2 millimeter scale. These two can be in a single chip, but simply we tape out the second chip in 2020 and the first chip 2021. So we don't want to re-tape out the second chip, so it's just a 2 chip, but we integrate them in the board and then test the functionality together. So with this interesting feature of the divisive normalization, we repeat the experiment that we did before. Previously, if I reduce the SNR below what is used for the training process, there was about 30% reduction in your accuracy, 20% reduction of your accuracy from 95 to the 75, right? But now, with this divisive normalization, we'll still be able to maintain my accuracy above the 90%, even the SNR of the 5 dB. So noise is actually louder than the sound in 5 dB case. And however, we still be able to maintain detecting the keyword. Okay, so now the unknown or different noise type, right? So we try different noise type, bus noise, metro noise, traffic noise, retro noise, and so on and so forth. And the blue bars represent the proposed work, the normalization circuit, and the red bar represent the conventional MFCC feature. And as you can see, over the board, across the board, the proposed divisive normalization improves the accuracy by as much as like 25% or something. So there's a significant improvement in this simple circuit, and essentially on my student on ICC paper, I guess. Okay, so the quick comparison. There's a multiple keyword spotting work, 2020 IACC, VLSI 19, JSC 16, and we also have this column of the no divisive normalization baseline that we created, artificially. Right, and then compare their performance here. And as you can see, actually not many work actually even present their accuracy at lower SNR level for different noise type, because they know that the result is not good, right? So this work actually present the fairly good amount of the data, and there was one work JSC 16 which actually bravely presents some of the result, and you can see that there's a significant improvement, about 25% kind of improvement accuracy, which is in the world of the machine learning is significant. Okay, so and finally the power consumption is about 200 nanowatt to 570 nanowatt in the bottom row. That's the combining everything to end to end. So these are the actually the one of the most power efficient end to end keyword spotting system as far as we know so far. So I go back to my first plot that I show in the beginning of my presentation, right? So this one kind of survey the total power consumption and the accuracy survey, right? And previously, VLSI 19 is one of the lowest power consuming end-to-end system, consume about 10 microwatt, accuracy about 90%. This IACC 21 work that done is by my student, Wei Wang, is actually achieve about 30x improvement in power consumption, whereas the accuracy is also going up above 95%. So very exciting, and that also put me into almost the last slide of my presentation. So I have a few concluding remarks. The first one is that although there's still a lot of challenge, the silicon artificial intelligence is getting closer to the biological artificial intelligence, and it's the small scale. So that's exciting. Second, divisive normalization, division, which is the taboo of this digital signal processing, actually can be very helpful, and you can do it with the spiking hardware fairly effectively. Right? The third one is the analog feature extraction, which is also non-conventional, but this can be also potentially, going into the very, extremely high power efficiency. And finally, again, non-conventional, relaxing the non-linearity constraint in the AMS circuit may enable a large amount of power savings. So most of the work that I present is actually work done by the three main people. One is Dr. Mingoo Yang, currently with the EPFL, Doi Wang, PhD student currently in Columbia University in my group, and Dr. Pavan Chundi, who is actually recently graduated and currently with NVIDIA. Okay, thank you very much, and I'm happy to take any questions if you have.
질문 있으시면 해주시면 감사하겠습니다. 네, 채팅으로 질문하셔도 됩니다. 제가 읽어드릴게요. 질문이
저도 지금 보고 있습니다.
네.
리니어리티와 노멀라이제이션이 서로 상충하는 개념인 것 같습니다. 리니어리티를 포기할수록 노멀라이제이션의 의미가 퇴색되는 것은 아닌지요? 이 질문은 제가 이해를 잘 못하겠는데 상충되는 개념인 것 같다. 글쎄요, 리니어리티는 제가 말씀드렸던 거는 이제 디자인, 아날로그 믹스 시그널 서킷을 디자인할 때 이제 리니어리티를 크게 신경 쓰지 않고 디자인하면은 회로가 좀 단순해지고 그에 따라서 파워 세이빙이 있는데 그게 이제 어큐러시에는 큰 영향이 안 줄 수도 있다. 노멀라이제이션이 입력 평균 파워로 나눠준다는 얘기인데 리니어리티가 깨지면 입력 평균 파워를 잘 못 재는 것은 아닐까요? 엄밀하게 리니어리티가 안 좋으면 입력 평균 파워를 잘 못 재는 것은 아닐까요? 그것도 맞습니다. 그러니까 말씀하시는 게 결국은 지금 서킷의 리니어리티가 안 좋으면은 나의 그 피처가 정확하지 않다라는 걸 말씀하시는 거잖아요. 그게 이제 우리가 생각하는 그냥 일반적인 아날로그 회로에서 생각하는 건데 사실 뭐 혹시 기회가 된다면은 간단한 익스퍼리먼트를 자기가 직접 해볼 수 있을 텐데 어떤 보이스, 오디오, 음악 같은 거 있잖아요. 음악 같은 시그널을 다운로드 받아가지고 그 스피치 프로세싱하는 소프트웨어로 그 밸류를 다 클립해 한다든지 아니면 간단한 매트랩 코드를 짜가지고 ADC를 난리니어하게 만들어서 한번 프로세싱해서 한번 귀로 들어보세요. 그러면은 정말 많이 디스톨트를 해도 보통 사람들 귀에는 그게 잘 이상하게 안 들립니다. 그리고 또 이상하게 들린다 하더라도 그 의미를 이해하는 거, 그러니까 노래 가사를 이해하는 데는 어려움이 하나도 없어요. 그러니까 지금 말씀하시는 거는 일반적인 스피치 시그널 프로세싱에 있어서 이제 리니어리티를 메인테인 하려고 하는 노력은 당연히 있죠. 왜냐면 그게 이제 하이파이 뭐 음악이라든지 이런 걸 할 때 항상 이게 중요시하는 거니까. 근데 그 어플리케이션이 그 음악을 듣는 그런 어플리케이션이 아니라 머신러닝 관련된 어플리케이션을 했을 때는 이 리니어리티가 우리가 좀 어떤 면에서는 오버스펙한 경향이 있다. 라는 거죠, 결국은. 그거가 그렇게까지 필요가 없는데 AI 펑션에 있어서는 리니어리티가 그렇게까지 필요가 없는데 그거를 약간 오버스펙한 경향이 있다는 거를 이제 밝혀준 거고 노멀라이제이션은 이게 약간 다른데 입력 평균 파워라는 게 그렇죠. 노멀라이제이션 자체는 이제 입력에 대한 어떤 그 노이즈 컴포넌트를 제거해 주려고 하는 역할인데 이거를 뭐 리니어리티가 정확하지 않아서 그 노멀라이제이션까지 노멀라이제이션이 하려는 것과 리니어리티를 컴프로마이스하는 거의 그 디렉션이 반대 방향은 아닌 것 같아요. 이게 뭐 이해가 서로 지금 뭐 이해가 됐을지는 모르겠는데 뭐 제가 답변할 수 있는 내용은 그 정도까지인 것 같습니다.
네, 교수님, 저도 질문이 한 가지 있는데요. 그 아날로그 피처 익스트랙션을 이제 하면서 그 앞에 이제 그 피처 익스트랙션 하는데 이제 밴드를 여러 가지를 이제 그 프리퀀시 밴드 안에 있는 에너지를 익스트랙션 하는 거잖아요. 근데 그때 이제 그 밴드 패스 필터나 이제 그 밴드 패스 필터의 컷오프 프리퀀시 이런 애들을 전부 그 패시브 디바이스 이용을 해가지고 예를 들어서 만들어주면 면적상에서 굉장히 손해를 보게 되지는 않아요.
맞는 말씀이시고요. 그 필터를 만들 때 이제 패시브로 만들진 않고요. 그 앰프를 써가지고 이제 그 앰프의 그 폴 위치를 잘 조정해가지고 이제 패시브랑 액티브를 섞어서 쓰는 거죠. 그래서 순전히 패시브로 하면 이제 시그널 스윙도 작아지니까 패시브로만은 하진 않고요. 액티브 앰플리파이어 같은 구조로 보통 디자인을 합니다. 저희가 했을 때는.
그러면은 그거는 면적은 대충 그냥 디지털로 구현을 했을 때보다 어느 정도나 증가를 하게
그 아날로그 필터 면적은 글쎄요. 그거는 사실 제가 그 슬라이드가 하나 있었던 것 같기도 한데 잠깐 제가 한번 찾아보죠. 왜냐면 컴패리즌 한 거에 필터를 컴페어한 게 있는데 필터의 그 에어리아를 테이블에 있었을 것 같은데 지금 굉장히 좋은 말씀하셨는데 저희는 이제 테이블아웃을 보통 한 65 나노미터나 65나 뭐 이 정도에서 지금 하고 있잖아요.
네.
최근에 28도 하고 있지만 그래서 아직까지는 제 생각에는 애널로그가 이익이 있는데 만약 이게 뭐 5 나노미터, 뭐 3 나노미터, 뭐 1 나노미터, 뭐 4in1 나노미터 뭐 이렇게까지 가면은 이제 디지털 쪽에서도 에어리아 면에서 상당한 이득이 있지 않을까. 지금 여기 나왔네요. 지금 에어리아 퍼 채널이 지금 노멀라이즈는 하지 않았지만 지금 포인원에서 0.1mm 스퀘어고 이 포인원에서 이게 디지털이군요. 디지털은 65에서 0.06934 그래서 이미 65 나노 정도에서만 해도 디지털이 어느 정도 개선이 있네요. 근데 이거는 이제 아날로그 투 디지털 컨버터가 포함되어 있지 않고 하나 있어가지고 LNA도 없어가지고 뭐 애플 투 애플 컴패리즌을 좀 하기 힘들고 정확하게 BPF만 컴페어하면 아마 이거보다는 조금 날 텐데 지금 상태로는 거의 한 10배 정도 차이 나는 것처럼 얘기가 나오고 아마 한 2배 정도 차이 나지 않을까. 다른 거 다 빼고 비교를 하면 그런 생각이 듭니다.
네, 알겠습니다. 네, 다른 질문 없으신가요? 네, 그러면은 그 훌륭한 톡 준비해 주신 성민국 교수님께 다시 한번 감사드리고요. 네.
감사합니다.
네, 감사합니다.